All right. Hi, everybody. So today we're going to go over the chi-squared mathematical equation for determining a statistical test in AP Bio. So this we're going to be doing in the context of a genetics unit. So this is particularly going to be using the example of rabbits because they are an easy to observe example of a dihybrid cross. So a dihybrid cross just means when you are crossing two different genes, two different characteristics, right? In this case, we are going to be looking at the two characteristics of long or short hair in rabbits and black or white fur. Short hair is dominant, long hair is recessive, black is dominant, and white is recessive. So when we're doing a statistical test, we need to kind of set up a scenario in order to understand what it is that we are testing. So let's say that this is the example we set up, okay? If these rabbits that we see on the screen, this black rabbit with short fur and this white rabbit with long fur, if these rabbits are considered purebred rabbits, meaning that they are homozygous for both traits, okay? So both of the traits, hair length and hair color, they're homozygous for both. What is the genotype and phenotype of the first generation, or in other words, the parent generation? All right. So the way that we're going to do this is we are going to do a quick example. So in order to determine the genotype and phenotype, remember you need to include the characteristic and you need to include their alleles, their allele combinations. So we have a black short-haired rabbit. So if that is homozygous, I want you to take a second to think, is that going to be big A or little a? All right. And I'm going through this pretty slow at first just because I want to give everyone plenty of time to practice. Okay. All right. So short hair is going to be dominant to long hair and black is going to be dominant to white. So that means that we are going to have an individual that is homozygous dominant for both traits. And this is going to give us a genotype of big A, big A, big A, little a. Oh, excuse me, big A, big B, little b. And then the phenotype is going to be short hair, black. Okay. Now, if we go back, we're looking at a long-haired white rabbit, which means, again, if we are thinking about their genotypes and phenotypes, this would be a lowercase a, lowercase b, and their phenotype would be long white. Okay, so just a little review of genotypes and phenotypes. All right, so now let's ask the question, let's ask a slightly different question. What are the possible gametes of these individuals? All right, so let's go back. We're going to ask, what are the possible gametes of these individuals? Well, the first individual, if we're making gametes from these sets of alleles, right? Remember, there's going to be crossing over that happens. There's going to be independent assortment, and there's going to be random fertilization with these gametes. So that means because of all of this recombination and this genetic diversity that occurs, the possible gametes that this individual can produce are only going to be big A, big B. Those are the only possible gametes it can produce. This A will either be in the same gamete as this big B or this big B. So those are the only options. For the recessive individual, it's a similar analysis. This individual will only be able to produce little a, little b, because this A is only going to be able to end up in a gamete with one of those two B's, because in order to form a gamete, you need to have half the genetic information, which means either this little a or this little a. They are not both going to end up in the cell. All right. Again, just a little bit of quick review. Okay. So this is what it looks like if we do a crossbreeding with the parent generation. So we've taken the gametes from the parent generation. This is the dominant parent. And then this is the recessive parent. So this is going to be our black short-haired individual. And this is going to be our white long-haired individual. We are going to produce individuals that are all the same genotype. Now, this is what scientists actually do. When they are trying to determine a genetic cross, they will take two pure breeding individuals that only ever produce the same of themselves, meaning they are homozygous, and then they will breed them together to produce purely heterozygous offspring. Okay? So in rabbits, again, this is just clarifying the genes. Short hair is dominant, black hair is dominant. So let's say that an unethical breeder, remember unethical being they are willing to pair very closely related rabbits together, paired two of the individuals from the last generation. So if we go back to this graph right here, right, this would be the F1 generation, okay? The F1 generation of rabbits versus the parent generation of rabbits. So what would be the possible gametes of the F1 generation? Well, if we take the F1 generation, right, and we're trying to figure out the possible gametes, well, we need to be able to say, okay, this A is going to end up with either the big B or the little b. So that means you can either get big A, big B, or big A, little b. And then this little a, whoops, this little a is going to end up with either the big B or the little b. So you can get little a, big B, or little a, little b. So those are your possible options for your gametes for this particular cross. Okay. So now that we know the gametes, what would be the possible phenotypes of the F2 generation? All right. So in order to figure out the phenotypes, we again, let me just quickly, I'm going to reorganize some things a little bit. In order to figure out the gametes, we need to figure out what would be the, in order to figure out the phenotypes, we need to figure out how this cross would look, right? So we're going to take big A, big B, big A, little b, little a, big B, and little a, little b. We're going to do a dihybrid cross, okay? And we're going to combine these gametes with the same gametes because they are both heterozygous. Okay, so I want you to pause the video and try to do this dihybrid cross for yourself. I'm going to show you what the first box would look like because again, you're just doing the same thing. This would be big A, big B, big B. The same thing that we've done in all of our crosses in the past. Okay, to take a pause on the video and see if you can figure out this dihybrid cross. All right, does your dihybrid cross look like this one? Double check your answers and see if it looks like this one, okay? Now, here's the tricky part about this. We need to be able to figure out the ratios of phenotypes in this F2 generation. So this is going to be our F2 generation. So what I want you to do is figure out, first of all, how many phenotypes are there? How many phenotypic combinations are there? How many phenotypic combinations are there? And then how many of each of those phenotypic combinations will you likely have? So let's try to do this together. All right. Big A, big B is going to give you what phenotype? This should be short. Oops. This should be short, black hair. Right? Let me just double check to make sure we're looking at the, dominant characteristic. All right. So big A is short hair, big B is black hair, right? Okay, that's this guy here. Next one, next to it, again, you have big A and big B. So that's going to be another short with black hair. So let's go ahead and make tally marks to indicate how many of each of these we have. All right, so we've got another, okay, short and black hair. Good. Another with short and black hair. Okay. Another over here with short and black hair. But then once we get to this guy here that I've highlighted in yellow, now we have a new phenotype. Now we have short hair with white hair color. Okay, what if we do this next one? Well, the next one is still short with black hair. So is this one. So we have two more short with black hair. If we do the next one, though, these are going to be what? Big A, excuse me, little a, big B, big B. This is a new phenotype. So I'm going to do this in a different color. This is going to be long hair with black fur. I just realized I also missed one down here. If we're looking over here at the very, very bottom, that's going to be another one that has short black hair. If we look at this guy right here, this is going to be big A, little b, little b. So this is yet again another, and I think I did this in the wrong color. Big A, little b, little b. Is that the same as all the genotypes that we've had so far? Well, it's going to be the same as the short white-haired rabbit. Okay. Can you guys kind of see, hopefully, where I'm going with this? The idea is we want to figure out what is our expected ratio of phenotypes in these offspring. Okay. All right, let's keep going through this. We've got big A, big B. So that's going to be short and black. We've got big A, little b. So that's going to be oops, wrong color. Big A, little b, so that's going to be short with white hair. We've got little a, big B, which is going to be long with black hair. Little a, big B, which is going to be long with black hair. But now we have a new phenotype. We have little a with little b. So this is going to be short, oops, excuse me, not short, long with white hair. So what would our phenotypic ratio be? Overall, our phenotypic ratio is going to be 9, and I'm going to use these colors intentionally. 9 to 3 to 3 to 1. Everybody tracking with me on that? Okay. So this is how you determine phenotypic ratios. First, you go through the Punnett squares and figure out what are your possible phenotypes. And then you go through and figure out how many of each of those phenotypes you have. So that is the process. Figure out the phenotypes and how many of each phenotype is possible. Okay. And this is going to be your ratio. Now, here's the tricky part. And here's where the chi-squared test starts to come in. Okay. If you have 1,600 rabbits, how many of each phenotype would you expect to have based on the ratio? How many of each phenotype would you expect to have based on the ratio? I'm going to give you a second to think about it. Okay, sorry about that. I was having some technical difficulties, so sorry for the very long pause. So when we're trying to figure out the expected frequencies of a particular cross, what you're going to do is you're going to take your total number of possible options. Okay. Now, this depends on how many traits you're looking at. If you were just looking at a regular Mendelian cross, you would only have 2 possible phenotypes, right? You would only have 2 possible phenotypes, but you would have 4 possible opportunities to get each of those variations in the phenotype, right? So that's what that regular 4-box Punnett square means. But because we're doing a dihybrid cross, what we have to do is we actually have to use 16 possible opportunities. So what does that mean? What do I mean by 16 possible opportunities? Well, when we're looking at ratios, what we're essentially saying is that this is a 9 out of 16 chance that you will get a homozygous, not homozygous, a dominant individual. This is a 3 out of 16 chance that you will get a dominant recessive individual. This is a 3 out of 16 chance that you will get a recessive dominant individual. And this is a 1 out of 16 chance that you will get a completely recessive individual out of this particular heterozygous cross in the F2 generation. Now, what you can do with these numbers is you can use these numbers to predict what phenotypic ratios you should see in a population. So if we took 2 heterozygous rabbits, we bred them together, and then we said, okay, now we're trying to figure out their phenotypic ratios. All you have to do is multiply these numbers by your number of total offspring, okay? So I want you to take a second, again, try to do this calculation, and then come back. We're going to put these expected frequencies into our box here, right? Okay. Now, just to be clear, we are not multiplying all of this by 1600. This is not a parenthesis here, okay? We are multiplying each of these values individually by 1600. Right? So this would be 9 divided by 16 times 1600. Now, I'm very much oversimplifying this. Some of you may already know the answer to this question, but because the numbers are not always going to be as easy as I made them in this problem, I'm showing you the stepwise progression, all right? Same thing for this guy. You're going to take 3 divided by 16 times 1600. You're going to take 3 divided by 16 times 1600, and then 1 divided by 16 times 1600. And again, a lot of you guys already know the answer to this, but I am showing you the process so that when you have to do more difficult problems, you know what the stepwise process is, okay? Hopefully at this point you can recognize that the expected frequency of short black-haired rabbits is going to be 900 short black-haired rabbits. There will be an expected frequency of short white-haired rabbits of 300. There will be an expected frequency of, let me move this around. There will be an expected frequency of 300 long white-haired rabbits and 100 long black-haired rabbits. Okay? Now, what does this have to do with chi-squared? Okay? Well, here's our actual results. Here's our actual results. So an ethical breeder breeds 2 known heterozygous individuals and gets the following results. Now, here's where the chi-squared test comes in. We have a question because these numbers, if we were to eyeball these numbers, right, they look pretty dang close to our 9:3 to 3:1 ratio. But how do we know that they're close enough? Because 289 is significantly lower than 300. So how do we know for sure that we are within the expected phenotypic ratios? This is where the chi-squared test comes in. Now, this equation looks intimidating. I promise it's very, very simple, all right? When we are analyzing this equation, this x squared value, this is the chi-squared symbol, all right? Now, this symbol here, the sort of funky looking E, this is the symbol for the sum of. So all that means is we're going to be doing repetitions of the sum of this equation. Now, O in this case stands for the observed frequencies, and E stands for the expected frequencies. Okay? O stands for the observed frequencies and E stands for the expected frequencies. So what you're going to do when you take the sum of something is you're going to take multiple repetitions of this equation for each scenario that you are interested in. Whether that's genotypes, because you can do this for experimental design, you can do this for genetics, you can do this for a whole host of different scientific analysis, right? Oh, I did that parentheses in the wrong place. There we go. Okay, so that's what the sum of means. It means that we are taking multiple repetitions of the same equation. And this is going to make sense once we look into our first problem. All right. Now, this is a great summary of the chi-squared test that Bozeman does. I encourage you to go back and watch this video on your own. Okay. Now, in order to do the actual chi-squared test, we have to form a null hypothesis. Now, we've talked about null hypotheses in my class before, but just in case you forgot what a null hypothesis is, it means that there is no significant difference between the observed and expected frequencies. Now, a chi-squared test, the results of your chi-squared test are trying to either support or reject your null hypothesis. So you're trying to either say, yes, there is a difference in the expected frequencies, or no, there is not a difference in the expected versus the observed frequencies. Okay? So this is our HO, our null hypothesis. Our observed values are not statistically different from our expected values. Our H1, in other words, our hypothesis, is that our observed values are statistically different from our expected values. So what does this mean for our bunny experiment, right? If we go back to the bunny experiment, we are trying to basically determine if the observed frequencies are being influenced by something other than Mendelian genetics. We're trying to look at these frequencies and say, okay, is there incomplete dominance? Is there codominance? Is there sex-linked traits? Because we can't always just look at the chromosomes and know for sure. It's easier to look at the phenotypic ratios. And that's what we're looking at in this experiment. So I want you to try to come up with a null hypothesis for the bunny experiment. Try to come up with one on your own. And remember, the key to a null hypothesis is that there is no statistically significant difference. That's your key phrase. No statistically significant difference. Got a null hypothesis? All right, let's see if you got it. This would be an example of a possible null hypothesis, okay? The observed phenotypic ratio is close enough to the expected ratio that we can assume Mendelian genetics and that no outside influence is occurring on the genes. In other words, there is no statistically significant difference between the observed and the expected ratios, okay? All right, so let's do step one. This is going to be the last thing that we do, and then I'm going to go into part 2 of chi-squared. So we're going to try step 1 first, and then we'll go into the rest of the chi-squared analysis, all right? First thing you have to do is input the observed and expected values into your equation and determine the sum of your chi-squared values. This is way easier than it seems, all right? I don't have a lot of room on my screen, so it might get kind of messy, but you guys should have enough room on your page, so you can do this on your page while you're taking notes, okay? So in order to determine the sum, we're going to take these first values, and I'm going to highlight these in red. And this is going to be our expected, our E, and this is going to be our observed. So we've got 901 minus 900 squared over 900. Okay? First one, done, easy. All you got to do is plug it into a calculator. Don't forget, you do get a calculator for the AP test. Okay, then we're going to add this to the next value. So we're going to take our observed frequency, which is 289, minus our expected frequency, which is 300, square that. Again, I apologize, I'm running out of space on my screen. And then we're going to put that over the expected, which is 300. Okay, we tracking? Try to do the rest on your own and see if you can do the rest on your own. You got it? All right, let's do it together. We are going to add our observed frequency, which is 304, minus our expected frequency, which is 300, squared over our expected frequency, which is 300. Okay, and then last one, final one, we're going to add all of this to our observed frequency, which is 106, minus our expected frequency, which is 100, divided by our expected frequency, which is 100. Okay, and this is going to give you your chi-squared value. See if you can calculate that. All right, I'm going to come back with the answer to our chi-squared value at the beginning of part 2. Now, in your practice problems, there will be chi-squared practice, and I want you guys to try to start with part 1. Don't try to move on to the other sections because it's going to be really difficult. And you can try to move on if you want, if you're up for the challenge, but don't get overwhelmed. I'm going to teach you how to do the rest of this. Just start with part 1 of the practice problems. Okay? All right. Have a great night.